Okay, now let's code. Now in this part, let's code the rotary positional encoding. And again, I'm not gonna use the Kai Gomez's code because I feel like it's simple to understand, but it's not as efficient as the one which is in Mistral. So the way that they do in Mistral code, and again you can have a look at it in their code base, is technically it should be right here in the rope. So they used complex numbers in order to do the rotary positional encoding. And again, if you don't know about rotary positional encoding, go back to my Mistral video. I explain it completely and thoroughly. Have a look at it and then come back. So yeah, I'm gonna use this piece of code there, and you're gonna understand how it works. So technically, again, we're gonna import torch, and we're gonna import, so this implementation is implementation from Kai Gomez, which I'm not gonna go according to that. We can import torch.nn as nn, and then what we can do is we can technically define something called pre-computed frequencies, and for that we need a dimension, we need the end is just the length of that vector for frequencies, and I'm gonna tell you what is those frequency in a minute. And then we have theta, and if you remember, let me just accept this. The theta was, we just defined it here, where is it, here theta, which is usually 10,000, and the output is just a tensor, and so on and so forth. So what we mean by these frequencies, if you go back to row former paper, which is technically the paper that they defined rotary positional encoding, and as you can see, it is pretty new. Mistral, Llama, and many more, and almost all the new large language models, they use this rotary positional encoding architecture. So if we go down to here, the definition of these rotary positional encoding over a vector. So as you can see, we have something called big theta, and this big theta is just those frequencies that we want to implement. I'm not going to go into details. Again, if you want to know more about it, go back to my Mistral YouTube video, more explanation over there. So these are the frequencies, so 10,000 to the power of whatever that this is, to this sequence length, this sequence length. And if you remember, we had something called end. This end is the same as this d, and so technically we want to have this frequencies vector, and as you can see, this is the explanation of it. And if we go back again, this is exactly the way that we define that in fact vector. So this is 1 over theta to the range of the 0 to to the half of the dimension, and 2 by 2. And if you look at it, this is exactly half of the dimension, 2 by 2. And the reason that it was 1 over something was because we have this minus here, and yeah, we have this t, which is technically for all the eyes. And what else I can tell you, the frequency, the outer, in fact the outer product of the t and the frequencies, and technically that's it. And then we turn it into polar, which makes it complex numbers. The reason that I like this implementation over the other one is because it uses, as I said, it uses complex numbers. And why we use complex numbers, so here is the reason. So as you can see, this is the result, the ending result. This r of the theta m is the final positional encoded vector of ours that we want to get. And this is that matrix. But if you look at it, and if you recall from the mathematics of uni or high school, so as you can see, it's a block diagonal matrix. And if I can, yeah, okay. So if you look at these blocks in this diagonal matrix, you can see that we have this pattern being repeated again and again and again and again. And if you look closely, so this is technically multiplication of two complex numbers, and that's all. That's why we use technically complex numbers in order to complex number representation here in order to make this matrix. So once we have all those frequency, pre-computed frequencies, which we're gonna use here in, as you can see, we have these thetas, and all these thetas come from here. So let me say that these thetas, all these thetas, they all come from here, and we computed them over here. And what we now need to do is just simply make these block diagonals, these blocks, and then just we have the rotary positional encoded version of a vector. So for that one, what we can do is we have something called apply rotary embedding. We have x, in fact q and k, and the frequencies. And then technically what we can do is just, yeah, and yeah, this looks okay. I'm gonna accept this and save it. So okay, the way that it works, so technically if we go back here, so where we use it, by the way, in the group query attention, we have this rope, and as I mentioned, the rope is being applied into key and query, not the value. So we have k and q, and as you can see here, we have k and q, and also the frequencies. And what it returns for to us is, by the way, we need to, yes, do this. We need to import tuples. And also it returns just encoded, positional encoded version of those two tensors. So what it does is we first need to view them as a complex numbers, and again, I'm not gonna go in full details. Go back to the Mistral video to visit and see how it works. We're gonna view them as a complex numbers. Technically it takes that vector 2 by 2 and turns them into a complex number representation. We do it for both q and k, and also we have these frequencies here. Once we have them all we need to do is just simply multiply them in a with a complex number multiplication. Once we have that, then we have the results, and then what we need to do is we need to return them after doing the complex number multiplication. After doing this, technically we need to return them into the real values, because we need each of these elements right here, and that's it. Technically we have the positional encoded version of the input, query, and key tensors. So yeah, and feel free to, if you have any more questions, feel free to ask in the comments. I will try my best to answer them.